Good morning, students. Am I audible?
Yes, sir, you're audible.
Yes, sir.
Yes,
Yes, sir.
Oh, thank you. My screen is visible. Is my screen visible to you?
Yes, sir.
Yes, sir.
Yes, sir. It is.
Okay. So, good morning, everybody. I will be teaching you induction machine, one of the very important machines of electrical engineering, very widely used in industry. Mostly it is used as a motor. Uh, just now we have covered the synchronous machine. So I'll be teaching. It is mostly used as a motor, induction motor, because of its construction. It is very widely used as a motor. Uh, like the synchronous machine is very widely used as a generator. So this is though the induction machine can also be used as a generator. We'll see that later. Uh, so induction machine, why it is very popular is that constructionally it is very simple construction. I'll compare. Very simple construction. Uh, Obviously, induction machine is an AC machine. AC machine. You know that broadly machines are divided into two categories: AC machine and DC machine. Okay. So AC machines are divided into two categories. One is synchronous machine. Another is induction machine. The other one is DC machine. DC machine is DC machine. Now there are a few modern machines. I am just writing it. Uh, One modern machine is called BLDC machine. That is brushless DC machine. Okay. There are some other machines called PMSM, meaning that permanent magnet synchronous machine. These modern machines, these BLDC and PMSM, particularly the BLDC machine requires the support of an inverter, that means power electronic hardware. We will learn about inverter in the next part, that means in the third year power electronics course. Inverter is a connection of the switches. It's a structure of the switches, semiconductor switches, put in such a way, in such a structured manner that you will be able to convert DC. Given a DC, you will be able to convert it into AC. So that's why its name is DC machine. The supply is DC. The basic supply is DC, but eventually you are getting AC. But this AC is not the conventional AC. What is conventional AC? Conventional AC is our supply system. Three-phase supply system has 415 volt, 50 hertz. These are conventional ACs. AC machines are essentially 415 volt, three-phase, 50 hertz machine. This is conventional. In America, it will be 60 hertz. Single phase AC machines will be taking supply from 220 volt. There are some single phase machines also, particularly single phase induction machine. So I should mention that induction machine also gets divided into two parts: three phase and single phase. Single phase induction machine, you know, very well known application of single phase induction machine is our fan, that in almost every household we have, and three phase machine. So three single phase induction machine will take 220 volt as 50 hertz as the supply. And the three phase induction machine will take three phase 415 volt line to line. When I mention 415 volt, I always mean line to line voltage. So that will be the supply of induction machine. Synchronous machine also, you have seen that it takes the supply from 415 volt three phase 50 hertz supply. So the modern machines I was trying to tell you, give an idea, which are nowadays very widely used in brushless DC machine is very widely used in electric vehicle application. So there the supply is, your core supply is DC. However, you are using electronic switches, semiconductor switches. Yes, hello. Is anybody trying to speak? Or okay, so brushless DC machine, as I was saying, that its supply is DC, but you electronically you convert into AC, electronic switch. You convert it into AC. So this switch combination is called inverter. And then from that AC you supply the motor, BLDC motor, BLDC motor. It is actually a three-phase motor. This is actually a three-phase. So naming it as DC sometimes confuses it because the supply is eventually it takes supply which is in the form of AC. May not be 50 hertz sinusoidal AC. The supply, another point is that always when you are referring these things, we are referring this thing as sinusoidal supply. Sinusoidal. Later we will see that the supply is square wave. SQUARE is square wave. So these are the differences with modern machines like BLDC machines. Permanent magnet synchronous machine is more like synchronous machine, conventional synchronous machine. Only the thing is that the rotor, you remember the rotor gets a DC supply. There is a coil in the rotor and rotor gets DC supply. It is excited by a DC supply. So that magnetic field is there. So that magnetic field in this case is produced by a permanent magnet. PM means permanent magnet. So this way, this is the development because of which the size of the machine becomes smaller, and such improvements, such kind of improvements you can see. Okay. So so let's come back to our main thought. The main thought is that we are supposed to learn about induction machine. So induction machine is called, another name of the induction machine is called asynchronous machine, asynchronous AC machine. So let me take one more page. So it is called asynchronous machine, asynchronous AC machine. That means synchronous AC machine and asynchronous AC machine. Why it is called asynchronous? We'll come to that. So this point you have to understand. This is what is making this machine fundamentally different from a synchronous machine. So before going to this aspect of it, we must all understand that what is the basic function of a machine, of an induction machine or a synchronous. What is the basic function? Basic function of a machine is to produce torque. That is the basic function. Speed doesn't come here. Speed is not coming here. This electrical machine is an equipment that produces torque, force into radius, that produces torque. The structure is such that it would produce torque. So torque producing equipment is machine, electrical machine. Now this torque production is the basic function. Is the basic and fundamental function of a machine. Basic and fundamental function. And in the process, what happens is electrical energy gets converted into mechanical energy. And so this implies that electrical energy is converted to mechanical energy, converted to mechanical energy. Okay, as in motor applications, or mechanical energy will be converted into electrical energy. As in generator application. So in both cases we will say torque is produced. Don't misunderstand me. Torque is produced, but when it is motor application, that means electrical energy is converted into mechanical energy, we'll structure it such a way that the torque would be considered to be positive. And when the mechanical energy is converted to the electrical energy, we'll consider that the torque is negative. So it's a convention of sign, plus and minus. But the basic variables that produce torque are unchanged. Basic variables, we will see that. Do you know what are the basic variables that produce torque? The basic variables that produce torque would be in a machine is flux. Flux means flux in the air gap. To be very specific, machine has a stator, machine has a rotor, and in between both of them are, rotor is a solid cylinder, stator is a hollow cylinder. Between stator and rotor there is air gap. So what is the value of the flux in the air gap? So the torque expression, first philosophically, this is the torque that is machine develops. Torque expression that's proportional to what it is proportional to, flux in the air gap and MMF of rotor current. MMF produced by the MMF of rotor current. Only rotor current. Don't take stator current. Only because torque is produced on the, and torque is both produced in the stator and rotor, but stator cannot move, it is frozen. So we are only concentrating on the torque that is produced on the rotor because that can move. So therefore, of the air gap flux with the rotor current and the angle between the two, and the angle, sine of the angle between the two, sine of the angle between phi AR and MMF, I write it as FR. So MMF of rotor due to MMF of not due to rotor current, let us call it FR. MMF this essential principle won't change. It will still remain intact, right? Only
Excuse
the
me, sir.
yes.
So you got disconnected for the last few seconds. So can you just repeat what you said?
I got now. Is it okay?
Yeah, now it is
now
okay.
So I was talking about the basic function of a machine, the basic function, root function, core function of a machine. No, don't say speed, don't say anything other than that. This is the function. Function is the produce. It produces torque. It produces torque, and during the production of the torque, it also helps to convert the electrical energy to mechanical energy, or mechanical energy to electrical energy. If the electrical energy gets converted to the mechanical energy, we call it motor application. If the mechanical energy is converted into electrical energy, we call it generator application. Okay, so how do you understand that what is when it is in the generator mode and when it is in the motor mode? How do you understand? Suppose I am giving you a machine. How do you know that from the core part? How do you know? For example, this is the torque expression. This is the torque expression. In all machines, it will be valid. What is the torque expression? Torque expression is flux in the air gap, okay, multiplied by the mmf of the created by the rotor current, and sine of the angle between this this flux and the mmf. Now, when I'm saying flux, what does it mean? It's slightly vague. What do I mean by mmf? In this case, if you go to the root part of it, root, absolutely first equation. The first equation will start with Q, for you remember the torque expression, that is Q V bar cross B bar into the radius, This is the basic torque expression. T, I should say T instantaneous, T expression, T of electromagnetic torque is essentially in one conductor. This is implying that this is happening in one conductor. And what is V? V is the direction of the movement of the current. So that and the flux density. Which flux density? Flux density that is cutting the conductor. That is cutting at that conductor, that particular conductor. So into the radius of the machine. So that is the first expression. Each one of the conductors. Suppose I want to know what is the torque developed in each conductor. You understand that the machine has a lot of conductors. The conductors are forming what? Forming coil, right? So I take a rotor, right? Rotor has some conductors. It is spread over the rotor periphery, rotor circumference, and I take each conductor, take one at a time, and just I look at it. At that instant, how much is the current? How much is the current? And the current is going in what direction? You understand that it is machine's construction is such that the current can go in only one direction. Current magnitude may change, but current direction cannot change. Is that okay? Do you understand that? If I make the statement, do you understand that? I am showing you why. Suppose this is the rotor and there is a conductor here. And the current is always, because of the construction, this is rotor. This is dot conductor, let us say, and this is cross conductor. So current is going what? Current is this, always this, right? Because of the construction. Direction of the current cannot be this. Anything is, the current is direction is moving along the length of the rotor structure, right? Or the length of the machine. This will be always, this current is going in and coming out. It is going along the length of the machine. And there is a flux density. There is a flux density. This is air gap. Understand that this is air gap. Understand that this air gap. This is air gap. I'm not fully drawing it. This is air gap. Okay. So the air gap. There is somebody else. This is flux density created by, we can say created by stator current, but we can also say that this is the flux density which is cutting the machine. That means this flux density is this vertical. This is the flux density I'm talking about here. This is the flux density I'm talking about here. And to make it more clear, I say this is flux density in the air gap. why I am making a distinction between flux density in the air gap and flux density in the stator? Can anybody say what is the difference between flux density? So
in the air gap, it is a resultant flux density.
It is a resultant flux density. And stator? And stator, flux density in the stator?
So it is only due to the current flowing in the stator.
Not quite true. A little bit clarification I will tell you. Flux density in the stator and flux density in the air gap is nearly equal. Flux density in the air gap is created by the current due to the stator coils and due to the rotor coils. And this flux path is also, what is the flux path? It is going through the air gap and it is covering the stator coil and it is also covering the rotor coil. So in the stator, it will almost see the same flux density as the air gap. A little difference will be why? Why? Because some of the flux lines will enclose the stator coils, but will not go through the air gap and link the rotor. So these kind of flux are called leakage, stator leakage flux, right? So due to this stator leakage flux, there will be slightly different flux density in the stator coil and slightly different flux density in the rotor coil with respect to the flux density in the air gap. But for all practical purposes, if we ignore the leakage in the stator or in the rotor, then we may say that the stator flux density, if I call it Vs, is very nearly equal to VAR, is very nearly equal to VR. That doesn't mean that Bs is created by only stator current, only stator current. That is not true. Stator current. If we think that this flux density in the stator coil is created only by, then it is not true. You know why? Because a coil, think about a coil, very ordinarily think about a coil. What is its flux linkage? This linkage is due to the current that is passing through it. But if somebody is also magnetically coupled, any other coil that is magnetically coupled, that is also producing the flux path. And this flux path, though it is not created by current in its own coil, is linked by this coil. So rotor current created flux lines are also linking this, because everybody has a confined path. Everybody has a defined path. This is what is magnetic structure doing. Fluxes are not going here and there. It has to be confined within the magnetic structure. That's why we have iron and a very small air gap. We are directing the flux lines properly so that it is created by, the fluxes that are created by the stator coils is not only linking the stator coil but also linking the rotor coil, majority part, because we don't expect too much leakage. So majority part. For simplicity, we can say full. No problem. To basic understand machine with essence, you can say that full. So these things are flux density wise they are equal, but MMFs are not equal. Stator MMF and rotor MMF are two independent things. This flux density has two parts. One part is due to the MMF created by the stator current, and another part due to the MMF created by the rotor current. These two MMFs together divided by the reluctance is what is flux, and flux divided by the cross-sectional area is the flux density, right? Same law, B is equal to mu H, and MMF divided by the reluctance. This reluctance is the reluctance of the air gap, creates the flux, and flux divided by the area is flux density, right? So so that is the thing. So what I'm trying to say, again coming back to the point that essential purpose of the machine is to create torque. And if I take conductor by conductor, this is the equation. This is the basic equation, Lorentz law. So this is the basic equation. But what is the torque in case of an induction machine or any machine which has a structure not only consisting of one conductor but many conductors? So then you understand what is that? What is your common sense says? Common sense should be saying that I have to add up. I have to add the torques in each conductor, right? over what? Over the space 0 to 2 pi angle. Every conductor, and this conductor is spread over an angle of 2 pi. So I have to take the torque in each conductor at a certain instant. There are other aspect is time instant. Let us say time instant is saying we were freezing in time. Freezing in time, and conductor by conductor, I am looking at the current direction. V is the current direction, which is always well defined. We know. And flux direction. The flux direction is also beautifully well known. That is the beauty of the structure of the machine. The flux directions in the air gap are always radial. Don't ever forget that. The flux lines are always radial, always radial. The flux lines are always this line. Some are going out like a north pole, some are coming in like a south pole. That is possible, but the lines are always radial, right? So here the flux lines are like this, and so on and so forth. So depending upon the current and current direction, the flux lines are either showing north polarity in one part of the space, and I'm showing the south polarity in the other. How the north and south polarity are defined as the arrow direction. Suppose you take a convention that rotor to stator arrow is north, then stator to rotor arrow direction is south. So this way. So what is the beauty of this machine construction is that as such each conductor, the angle between V bar, this direction, this vector, and V bar is always 90 degree, and therefore let us call torque here also as a bar, and the torque will be using that right hand law of two vector products, V bar cross V bar. You can use the corkscrew law. Move V bar, take a screw and move the put two lines, one indicating the V bar direction and another indicating the V bar direction, and move your screw from V bar to V bar direction. Then the resultant movement of the screw, which is a right hand screw, you are using right hand and moving from V bar to V bar in that manner, in that direction, and the resultant movement of the screw will be showing the direction of the torque produced. So that we know, that Lorentz law. So we know that. So this is for every conductor. So what is the difference in the machine? Our common sense is saying that the difference will be that we have to add for every conductor, because there is not only one conductor, there are many conductors here. Maybe one conductor here, maybe one conductor here, maybe one conductor here, so on and so forth. So there may be one dot conductor here and dot cross, so on and so forth. So everywhere we have to do this, compute this torque and add them. So so you understand that what we ultimately get at a certain instant is the average torque. Now, why this average torque will be different from in each conductor? Why will it be different? Can you tell me why it will be different? Conductor by conductor, why the torque will be different? Because you will see that the MMF pattern is not constant over the space. It is a sinusoidal pattern. The flux density pattern is not constant over the space. In our machines, we are creating sinusoidally distributed flux density in the air gap. We are creating sinusoidally distributed MMF, rotor MMF pattern in the air gap, in the space. We have created such thing. So eventually what we would be getting is a kind of integration, and this integration of these two sign quantities, you already know, depends the average value. So this is nothing but torque average torque at a certain instant in the machine. Not this one, I will take it average. This average torque at a certain instant will depend upon the sine angle between the MMF and the MMF is this, FR is the MMF, and the air gap flux, air gap flux, this angle, the dimensionally this becomes phi AR. So never forget the dimension of this torque. Phi AR into FR into sine of the angle between phi AR and FR. What is phi AR? Phi AR is, when we are drawing as if it is a phasor. What we will draw? We will draw it like this. That means this is the peak of the phi AR. At that, after that, this is sinusoidally distributed in the machine. So this and MMF, rotor MMF. Let us say this is I'm drawing and converting into the idea of a phasor, but this is a space phasor. Must not understand, take it as a time phasor. This is how, this is theta. This variation is with respect to theta. That means sinusoid, then with respect to theta. This peak is at this instant is there, and then over the and sinusoidally distributed over the space theta. This is we said that it is MMF, that is rotor MMF, FR. This also has a peak here, at this instant peak here, and then angle, and then sinusoidal distribution. And the angle between them is called delta. Delta. See, delta R. Let us call it delta R. Did I say anything? No, delta. The delta R is the angle between the two. And if this is the angle between the two, then the average value will depend upon sine of the angle, sine delta R. That is the peak value of, this is peak value. After this, average value will depend upon this phi AR peak, the sinusoid's peak. It will depend upon the MMF's peak, and FR. This exactly comes from integrating this equation. It requires a little bit of derivation. At this moment, that is not important. Important is to get the idea. It is simple derivation. You can do a derivation. You can yourself write to sinusoidal expressions and integrate it and see, convince yourself. It is easy to convince yourself that this will be the magnitude of magnitude means peak value of the flux density waveform, peak value, not flux density, peak value of the flux waveform into peak value of the MMF waveform, rotor MMF waveform, and the sine of the angle between these two. Is anybody has a question up to this point? Is it okay? Do you understand what I am trying to say? Amritaksha?
Yes, sir, it is clear.
It is clear, right? It is clear. So, right. So if that is clear, let us take this a little more conceptually in another picture. Another picture I want to take it a little more conceptually is that let us take a machine. What are you trying to do then? As I said that I will be looking for flux in the air gap, creating flux in the air gap, and creating rotor MMF. So they are, in another words, nothing but creating They are nothing but creating two pole pairs, one for stator and one for rotor. Magnets. We are creating as if two magnets. That is the essential interest, and these magnets would like to align, and the intention to align will be termed as torque, production of the torque. So so let us say just before that, one more little more idea I want to take. So I have said that T average in a machine, I am now taking as a dimension, as a scalar quantities. So because it is magnitude, what is important? Direction we already know. Because of the construction, because the flux lines are always radial, and the current is always going vertically down along the length of the machine, the torque direction is unchanged. It is circular direction. It will be producing torque. So torque direction is all adding up. Directionally, it is all adding up. Only the magnitude is important. So that the magnitude average is, as I said, is phi AR. Obviously, to make it more clear, peak. Understand this as peak, and then MMF of the rotor peak, and the sine of the angle of between these two peaks. Okay, in the space they are sinusoidally distributed. This is the sine delta R. Okay, so now from here I have given you the equation. Then how do you construct a machine? How do you think? Who decides this phi air? Who decides phi r? It is still very vague. How this is getting related to the mechanical thing, because the torque means if I just produce a torque and there is no load, then the machine will continuously accelerate, isn't it? And because the fundamental law of mechanical energy is J d omega mechanical by dt is equal to T E average, T average E, let us say, or T E average, T E average minus T M. M is the mechanical load, isn't it? There has to be ultimately a balance. Otherwise, the speed of the machine will always increase. The speed of the rotor will increase. We have developed a torque, but there should be a counteracting torque also. Otherwise, how the machine comes to a constant speed? In order to come to a constant speed, it implies that d omega m by dt has to be 0. D omega m by dt has to be 0 under steady state. Under steady state, this has to be 0. This is the basics, mechanical engineering. So, as I said, machine is an interaction between electrical and mechanical. Just electrical cannot decide everything. Mechanical has to be given its role, and the mechanical role is damping it. It is putting a kind of counteracting torque on the rotor. That is a mechanical load's property, right? That is mechanical load's property. There it could be fan type of load, pump type of load, and they have different characteristics. What kind of characteristics? When I say mechanical load characteristics, what do I mean by this? It also has a torque versus speed characteristics. Mechanical load has torque versus speed. Let us say one mechanical load characteristics may be like this. This is mechanical load and this is mechanical speed. There may be a characteristics like this. So there is a characteristics like this, and electrical torque is produced by as per this relationship, right? So so at a certain point, if at all it comes to steady state, what has to happen? It has to happen that the electrical torque has to come to be equal to this value. So let us say the electrical torque is this. E average is this. So what it means? That means that it will dictate the speed at which the machine has to operate. This must be the speed at which, and sometimes I will not say that. You understand that the angular speed is this. I always cannot say that angular speed at which the machine would operate under steady state. So this is the way electrical and mechanical things interact, and eventually machine achieves a certain speed. Steady state. It is called steady state. Steady state because there is no differential. This differential equation, the quantity, right hand side quantity is 0. It is neither accelerating nor decelerating. It has reached that speed and it is happy. Okay. In real life, it never happens, but mathematically it happens. In real life, maybe a slight variation is there for some small reasons. So that is not to be considered here. We are understanding the essence. So this is what decides the speed of the machine. So what we have decided, the speed of the machine has been decided. Is there any other constraint imposed on the machine? Any other constraint imposed on the machine? Can anybody give me a hint which decides phi AR or phi FR or delta R? Is there any constraint that is imposed on the machine?
So power.
Power, how do you deploy? Can I say from the supply 10 kilowatt power? I cannot say that. I connect the machine to a supply. I cannot dictate the power. Power gets dictated with complicated interaction. Power, how is it getting dictated? Because eventually the power is equal to Tm into omega m.
So the frequency.
Frequency is one constant, but how is it related to the torque expression that I am writing? I just want to know what will be the flux, air gap flux. I just wanted to know what will be the MMF, peak value of the MMF. And I just want to know what will be the delta R.
So length of air gap.
That is think
The current.
ordinary. Current, who decides current? Can you, our sources are always voltage sources, they're never current sources. How can you dictate current? You can dictate voltage, you are right. Only thing that you can dictate voltage. Voltage where voltage means where? The voltage that you are applying to the coil, the at least stator coil. Rotor coil may not be accessible. In an induction machine, rotor coils may not be accessible. There are two types of induction machine. I'll come to that. But let's forget that. Our basic point where we inject our electrical constraints is the stator, the basic terminals, and the terminals that you inject in a normal application where there is no inverter. Inverter has an electronic way of injecting voltage that we require, an electronic way of injecting the frequency that we require. But you forget that. That is electronics. That is inverter electronics you learn in the third year. In a conventional application, in a conventional applications, the only way we can impose electrical things is by giving a voltage. Agreed or not? Just simple statement, do you agree or not? Yes?
Yes,
sir.
Yes, sir. So you can apply voltage. So let us see how voltage dictates. Can voltage dictate any one of the things? Can it dictate FR? Can it dictate phi AR? Can it dictate sine delta R? Can it dictate anything? Tell me what it dictates. One thing very clearly. Can you tell me what? The moment you say voltage, voltage means voltage magnitude plus you are also saying frequency. So what are you dictating then? And the coil, giving a coil. So what are you dictating there?
So means if I apply a voltage across a coil in terms of resistance, I am dictating the current. Means
No,
across.
no. You are not dictating current. You are not dictating. Current will be dictated by the load, by the torque that is produced, by the speed at which it is reached. Take it on more ordinarily. What is the first equation you have learned to relate voltage to flux? Have you not learned the equation to relate voltage to flux? V is equal to Nd∅ by dt, Faraday. When you apply a voltage across a coil, the Faraday comes in. The first basic principle comes in. It has to happen under any condition, any current, any load, anything. It has to happen. Voltage means your N∅ by dt is decided. N is the number of turns, which is a physical quantity for a machine. Stator, it is not dynamically changeable. So you can take it as a constant. So what is then decided? d∅ by dt is getting decided. And assuming that the voltage is sinusoidal, what has to happen? The flux is also sinusoidal, right? Sinusoidal or cosinusoidal, right? Then what happens? The magnitude of the flux, does it not get decided? You have derived that formula, no? If I remember it correctly, what is the formula you have derived? That induced EMF is equal to what? Flux per pole into omega electrical into total number of turns n phase, and then sinusoidal function. I am talking about the magnitude now, peak magnitude. So peak magnitude wise, is it not this? Do you remember the derivation? Professor has definitely have done this derivation, right? A voltage induced in a coil. Hello?
yes, sir.
Yes, sir. So what is this flux? This is the flux in the air gap. The moment you are applying a voltage, it is related to the flux linked by the coil. And I said that let us ignore for the time being the leakage flux. So the flux linked by the coil, the stator coil, is the same as the flux in the air gap. So this quantity gets divided, provided omega is constant, and omega is constant. Our supply system is normally more or less constant. Take 1 or 2% variation in the frequency that happens. That is essence. We are learning essence all the time. So this is the induced voltage in the phase, E phase, right? And what is the difference between E phase and V phase? If there is a little bit of difference, again we will ignore it. V phase is equal to R phase into I phase plus, maybe you can say phasor wise, you can say J omega L leakage phase into I, you can say plus E. This is the basic equation. This is the basic coil equation. If anybody has any problem with it, tell me. This is the basic coil equation of a where AC supply is applied, and I have written it in phasor form. I have written it in the
Sir, R phase, I phase should be equal to E plus J omega Li, right?
what are you saying? R phase, I phase, what?
So R phase, I phase is equal.
No, here I am talking just R phase. Let us take one coil at a time. See, the approach is not to combine so many things together. I know whatever happens in R phase will happen in Y phase after 1 just there will be phase shift of 120 degree. The V phase itself will be 120 degree shifted in the case of a Y phase in respect to R phase. So let us not complicate. Let us take R phase equations. This is R phase.
So this is for motor mode na? Means this equation is for
This
generator.
equation is valid for motor mode, generator mode, transformer mode, any mode. There cannot be a two different equation. Faraday's law cannot give you two different equation, and there cannot be two different Kirchhoff's law equation. This is the Kirchhoff's law equation. Basic structure is a Kirchhoff's law equation. E is given by the Faraday's law equation. E is coming from n d phi by dt, and this has to be d phi by dt. If you dictate phase, so what are you dictating here? Electrically, you are dictating phase voltage. You are not arbitrarily letting somebody choose the phase voltage. You have dictated this. This is dictated. This is dictated because of the supply. So if you dictate it, what are the consequences? I will simplify. You let me simplify now. I say that the coil R phase is equal to 0. Let me simplify. Let me simplify that LL phase equal to 0. Simplify. These are simplification I will do. Because leakage inductors, I can easily think that machine is ideally constructed, no leakage. I can think that. And it is qualitatively, these drops are very small. R phase, do you want the machine to have a lot of resistance? Why do you want machine to have a lot of resistance? Machine coil to have a lot of resistance. Resistance is the, if you have lot of resistance, then the drop happens within the machine. How the power will go to the mechanical side? It's a common sense. We don't want machine to have lot of, that's why we put very good copper. Why do we put copper? So that the coil resistance is up. Don't misunderstand power here. This is a lossy power. R phase is having power, this is lossy, that is unuseful, that we don't want. But it will be there. That is life. Even if we don't want some, however small, however insignificant, it will be there. So if we want to do it very accurately, we'll put it. But there is a place for accuracy. There is a place for accuracy at some other point. Okay, here this is not the place for accuracy. This is the place for understanding essence, understanding the interactions between different variables in a machine. Whether it's a generator or motor, doesn't matter. This equation is always valid. V phase, maybe I direction will reverse, but that I can handle by using phasor. This is the convention I have taken, is this I here. That doesn't matter. If I take I 180 degree shifted, that makes it negative, right? So a convention way of putting is that this is what is V phase I have applied. Their machine and the induced EMF is E, which we cannot physically catch. We cannot measure. It is there. Induced EMF in the coil, that is E. That is due to the rate of change of flux linked by the coil. And this flux is a stator flux, ideally. That's why we have split it into two parts. One part is the leakage part. This is the leakage part. We have split it into two. And this part is the mutual flux. And then we'll say that, let us say LL phase, that is the leakage inductance, is not so significant. And therefore we ignore it. We say that. No problem, should not be a problem. So therefore we say that V phase, this is dictated, is dictating what? Dictating E, the induced EMF of the phase of the coil. Each coil, this equation is a coil by coil equation. I can write similarly another equation for Y phase. it will be identical looking, because phase current will be R phase current. Here in this case, phase current will be Y phase current. Induced EMF will be R phase corresponding to this phase, and other case it will be corresponding to that phase. That is not a very important one. So you should know, you should not confuse sometimes we unnecessarily confuse ourselves and try to think three phases together. But most of the equations are fundamental equations. They are valid for each phase as well, has to be, because Faraday's law cannot be different for single phase and for a three phase. So for even in a three phase there is a single phase, right? So this equation must be valid, and V phase is very nearly equal to E phase, very nearly equal to E phase, which essentially means what? E phase has to be related due to Faraday's law by this expression. So therefore we see that when V phase is given, what we are essentially making constant is flux air gap. This part of the this phi p suffix p is for pole, flux per pole. You professor must have done the expression for that. Ultimately the derivation flux per pole comes because the machine may have more than 2 poles. Unnecessary complication at this point. These are just coefficient, just adding, multiplying coefficient. You can handle that. That is not a big deal. That is a meticulousness. But the philosophy of this is that the moment, you never should forget, the moment you apply voltage, you essentially dictate the flux of the machine, and flux of the machine is nearly equal in stator, rotor, and air gap. MMF is not equal. MMF is created by the stator, MMF is created by the rotor. Combined MMF is creating the combined flux. That is the point, right? So flux of the machine is now this way dictated. So in the torque expression, therefore, which part is getting dictated due to voltage is, this is due to voltage, it is getting dictated. This is voltage related. Then we are having this play with this. Now you come see that the difference between synchronous machine and induction machine will come here. Tell me in synchronous machine, what is FR? Tell me, you have just studied that synchronous machine. What is FR? MMF of the rotor, what is it? Can you make a comment about that rotor MMF? Amritaksha, make a comment.
Yes, sir. It will be like if I2 is the current in the rotor, it will be I2 and N2.
Yes. What it means, and current is a DC current and normally kept constant, right? As long as it is kept constant, FR is constant.
Yes.
Yes, because you are passing a DC current in the coil. How is rotor MMF created? By passing a DC current, and DC current, as long as the DC current, you are not doing field awakening, this, that, all those things for the time being you ignore. As machine can operate, develop different torque, having the same rotor current. So FR in a synchronous machine is just, FR is the MMF, NR magnitude wise into IR. This IR is DC. IR is equal to IDC for a synchronous machine. For synchronous machine, IR is equal to IDC, right? So how then this machine, synchronous machine, develops different torque? Tell me which parameter has to change? Which parameter needs to get adjusted to produce different torque? Because we have already put a constant on the phi AR. We have already put a constant on
delta.
Delta. So that is what is the synchronous machine's torque angle, load angle. That's why it is called load angle. That means depending upon the mechanical load, a new set of operating point will be decided such that this new torque will match the mechanical load torque at a particular frequency of rotation of the rotor. So this way, is that clear that synchronous machine is when it is loaded more or less is actually adjusting the delta to more or less? Synchronous machine, because synchronous machine has constraint. Synchronous rotor current has been frozen. It is a DC current and I am just controlling it. I am passing 40 ampere DC current. Done. But the machine has to produce torque. How will it do it? Why the machine has to produce torque? Because unless that torque is produced, it cannot balance the mechanical load torque. It cannot balance, right? So that speed, if is dictated, in fact, I will give you a more interesting, more insight into it. The mechanical speed is dictated by the application. Take a steel plant. There is a conveyor belt. Somebody, the process control fellow will say, I want the conveyor belt to run at 20 meters per second, right? So that thing will be converted into from linear speed to angular speed, and the m will be decided. Then that m, omega m, will decide as per the conveyor's load characteristic. Conveyor is a mechanical stuff. No electrical is coming here. Conveyor's speed torque characteristics will decide what has to be the mechanical torque. And therefore, to develop this torque from an electrical machine, the electrical machine has to develop that torque. So its speed is already decided, its torque is also decided, because speed is decided by the application, and the application and the conveyor belt characteristic has decided the mechanical torque, and that mechanical torque has to be balanced by the electrical torque and the steady state. And the electrical torque, if it has to be balanced, electrical supply system is already decided. So the flux is decided. You have not changed the field current of the rotor, so that is also decided. So what is then in play? The only thing that is in play is delta R. So the machine will adjust their angles between this. Okay. In electrical term, how will you see? If this angle changes, what will you see? You see that flux and the induced EMF are orthogonal, right? If flux is sine theta, this thing is cos theta. d phi by dt is cos theta. That means voltage is cos theta. That orthogonal, 90 degree apart. So the current, now the voltage is this, and the this thing is this. The rotor MMF is this. That angle you will be seeing there is a difference. There is a change. That is the thing. Electrically, you will see that the voltage and the current will be changing. Will be making a adjusting itself, and the power factor will be adjusting itself to formulate this VI cos phi. From electrical power point of view, VI cos phi has to be equal to FR sine delta R. Okay, I will come back to that in a so this is how you will realize it, because internally we do not see the flux, we cannot see it. It happens, it will happen, this angle will happen. Achha, just quickly, Amritaksha, tell me, the torque equation remains the same. What way induction machine will operate? You tell me. If you can think of, I'm giving a hint that induction machine, this delta R angle is always 90 degree. I'm giving you a hint that induction machine case, there is not possible to have, because induction machine, there is no other source through which you can inject a current in the rotor current. The rotor current is a reflection of the stator current, like a transformer. It is a reflection of the stator current. So induction machine, in order to produce more torque, what will it have to do? It will have to therefore adjust the magnitude of FR. The magnitude of FR was unchangeable, ordinarily speaking, in a synchronous machine. But induction machine, delta R will remain 90 degree almost all the time, 90 degree. But in order to adjust to the new value of torque as per the demand of the load torque, it will adjust the FR part. FR means current value. FR part is that it will adjust FR for induction machine adjustment. That means current. FR is N into I. That means the rotor current will change. And rotor current changing means stator current will be changed because of the fundamental relationship between N1 I1 plus N2 I2 is equal to N1 into I0. I0 Im is the magnetizing. And that fundamental relationship will always, if the rotor current changes, stator current will also have to change.
Sir,
Yeah.
Sir, means I have a question. Sir, means when we are finding the torque, the thing that will come into account is the angle between the rotor field and the flux in the air gap, right? Means sine of that angle.
Angle between not rotor field, rotor MMF
Rotor
and
MMF.
the rotor
Flux.
MMF and the flux in the air gap. Yes.
And sir, means but delta is the angle between the means bus voltage and the induced EMF. So how these two angles should be equal, means will be equal as well.
I will show you. You are just taking 90 degree shift, and eventually the angle between them becomes same. That I can show you later. So they become same because flux to voltage is 90 degree shift. Okay, MMF to current is a 90 degree shift, and then they become equal. Flux to voltage is 90 degree shift. Is that okay?
Yes, sir.
And MMF direction and the current is also another shift. So these things ultimately becomes a there the power is VI cos phi, and here the angle is 90 degree minus phi. So therefore it is sine of delta. Power is what? VI cos phi, right?
Yes, sir.
So V is where? 90 degree with respect to this.
Yes, sir.
Therefore, this is between the delta angle between phi and f. Okay, the time is over. I will explain that in the next class after drawing a figure. Okay, thank you very much. I am closing now.
Thank you, sir.
Thank you.
Thank you, sir. Sir, stop recording.
What is that? Thank you.